So let's look at molecular lab number 68, which deals with the melting transition at the molecular level, because this particular experiment allows students to easily visualize two things. First of all, it will allow them to make a microscopic or atomic level versus a macroscopic comparison of properties. In this particular case, the density of solid ice as opposed to liquid water, and it will also allow them to visualize the dynamic nature of the melting transition, which will allow students to start removing misconceptions of things such as bonds breaking during phase transitions as opposed to intermolecular forces being overcome, and it will allow them also to visualize, in a sense, the transitory nature of intermolecular forces, the fact that they're dynamically broken and formed over the lifetime of an experiment or over the lifetime of a sample of liquid water or solid ice. So what we see on the right hand side is that we can look at the water, or in this case the structure of the ice itself, in two different molecular styles. Right now as a default we are set on ball and spoke, and we can also look at the water or ice, the water molecules, in a tube representation. This is very important here because you can quickly see the alignment of the water molecules in the solid state. And what's fascinating is one can see right away that there is a very regular arrangement of water molecules. Now, why does that particular arrangement exist? Well, in previous experiments, we have looked at specifically with either one or two water molecules the dynamic interplay of hydrogen bonding and how hydrogen bonding allows the water molecules to align in a specific fashion when we're dealing, for example, with the water dimer. So let's visualize the hydrogen bonds here and see how they cause the water molecules to line up. So I'm going to go to show under hydrogen bonding, and we can see right away if we zoom in on one or more water molecules in the tube representation that here we have a representation of the hydrogen atom, which I'm going to go back to the ball and spoke phase to see. So here's one hydrogen atom, and you can see it's perfectly lined up in a hydrogen bond with respect to an oxygen atom on another water molecule. So if we zoom back out in both the ball and spoke representation and in the tube representation, we can see right away that in order for hydrogen bonding to take its maximum advantage in the sample, the water molecules must line up effectively in these ring-like structures. And as a consequence of having this ring-like structure, the overall density of ice must be relatively low because we effectively have these cavities between these water molecule rings that are empty. So therefore, for a given mass, the volume is significantly high from right there. If we dynamically run the sample, we can see at the temperature of the experiment, which right now is negative 173 degrees, at the temperature of the experiment, the water molecules do not have enough average kinetic energy to begin to overcome these strong hydrogen bonding interactions. So although the perfect nature of the rings are deformed when we're actually running the dynamic simulation, we see right away that the rings themselves are stable. And as a consequence of that, the density of the system stays constant. And of course, we have a beautiful sample here of a solid water from right here. Now, one thing we can do as an aside that's not specifically listed on the right hand side is that we can view this a slightly different way, and I like to do this quite a bit when we're looking at solids to emphasize to students that in the solid we really maintain that definite shape. So in order to do that, what I'm going to do is I'm going to go to view or edit, go to select group, and I'm going to select all the water molecules in the group. Then I'm going to hide them. So although they're there in the system, although we can't see them, and then I'm going to turn trails on for the system and run the system right away. And what's happening now is that the center of each water molecule is being visualized. We're actually watching the motion of the center of each water molecule, although we're not seeing the specific atoms. And we can see at negative 173 degrees Celsius, there's still a significant amount of vibrational motion that's occurring for each water molecule relative to its other water molecules, but we are definitely maintaining the lattice shape of solid ice. So this allows us to really just visualize the center of each molecule and really say, hey, this is what we mean when we say definite volume and definite shape. The water molecules themselves are effectively locked in position by the strong hydrogen bonding interactions. So I'm going to go back and revisualize the system. We'll go back to, in this case, tube, and I'm going to turn off the trails here because otherwise they will get in the way. And now let's see what happens to the water molecule sample, or our sample of ice, when we increase the temperature. So here we're going to increase the temperature very quickly by 200 Kelvin to take it from negative 173 degrees Celsius to above the melting point of ice, or the melting point of water. And let's watch what happens dynamically when we increase the temperature. So right away, since temperature is measuring the average kinetic energy of the system, the water molecules now have a significantly higher kinetic energy than before. And as a consequence of that, we begin to see that the hydrogen bonding network is much more disordered than before. We have lost that beautiful repeating ring pattern of in the samples of the water molecules, and now we have a much more disordered pattern from right here. As a consequence, we can see too that effectively the average position of the water molecules themselves is slightly dropped relative to the ring structure. We've lost those holes from one water molecule to the next, and since that hole structure has been lost, effectively the density of the system has increased. We have more water molecules in a slightly smaller volume. So therefore the density has gone up relative to solid ice, and as a consequence of that we would see the water sink, or equivalently a sample of ice relative to here, to float on the sample of liquid water on top of that. So right away we can see that simply just by increasing the average kinetic energy, we lose that beautiful structure, increasing density, and causing a sample of water to sink relative to a sample of solid ice.